So in order for the simple pendulum to approximate simple harmonic motion, it has to obey some form of Hooke's law, right? The force has to be directly proportional to the distance it's displaced from equilibrium, and it has to be in the opposite direction, so always pointed towards equilibrium. So let's look at a pendulum. Out at its maximum swing, there's some mass. There's the vertical. This is the path that the pendulum would take, all right? And let's take a look at the force on our pendulum here. Well, the force is going to be the force due to gravity. All right? There's the weight of the pendulum. And then also there's a tension force. Ft right there, okay? So if we look at the force that is bringing it back towards its equilibrium position here, all right, that's going to be, well, this component of those two forces, okay? Or this component of the gravitational force, as it were. That component's going to be its mass times the acceleration due to gravity multiplied by sine of theta, where theta is this angle, and we can see that if these are parallel lines, then that angle is also theta, or the amplitude in this case. All right? Well, how does that fit into Hooke's law? Right? We've got F equals mg sine of theta. There's no linear distance here. Well, if we take a look at what we've got here, we can approximate this with the arc length there, all right? We talked about this approximation where for very small angles, the sine of theta is equal to theta itself, right? Maybe not equal to, but again, this is an approximation. And that's a very, very good approximation within 1% for anything as long as theta is less than 15 degrees. Now, that runs down to about, 0.2617 radians. All right? And so as long as theta is less than that, we can approximate sine theta as theta itself, okay? So this becomes the force equals mg times theta, as long as we have that condition applied to it. So it's looking a little closer like something that would resemble Hooke's law. And remember that if theta is measured in radians, as it should be, then theta is going to be the arc length, theta is the ratio of the arc length to the radius of the circle, right? Let me make sure I got that right. Arc length to the radius of the circle. Yes, okay. Now, for very small angles, it's not a terrible approximation to approximate S as a very linear distance, right? Imagine zooming way into that and you'll see it looks very flat, right? Very much like Earth, the flat Earth. That's why people think it's round, right? Because they're like, oh, if you just zoom out, you can see it all round, okay? Neither here nor there. All right, well, S in this case, we're approximating as a straight linear distance. R we're approximating as the length of the pendulum itself, that's the radius. So we'll put that in here, and we've got F then equals mgx over the length. Now in this case, when we do this, we can just do a little reordering, and we'll see that F is equal to mg over L times x. All right. We can see too that it would be in a negative x direction as the force is positive. Positive? Well, the magnitude of the force is positive, right? Force, yeah, okay. Either way, we've got some constant value here because if we're looking at the same pendulum, the mass isn't going to change while it swings and the length isn't going to change while it swings. So we've got a constant value here, and we've got that direct proportion to the force in this case, all right? Now, what that means is that K, the constant which for a spring is the spring constant, for a pendulum is something a little bit different. It is mg over L. Now, if we take this and put it into the period of a mass spring system, right? If we do this, if we insert K in here, over like so, all right? One more simplification here. We've got m times L over mg, right? So that's multiplying by the reciprocal there. We'll see that the mass doesn't actually matter for a pendulum. Okay, but what does is the length and the acceleration due to gravity. In the end, we've got a period of a pendulum which is 2 pi L over g with a direct square root relationship between the length and the period and an indirect square root relationship between the acceleration due to gravity and the period. So what we want to know then is, well, why doesn't the mass matter? Okay, and why doesn't the mass matter? Well, take a look at your pendulum. What is the driving force of this? It's not the tension, because if I took this into the far reaches of outer space and let go, well, what would happen? Not that, nothing would happen, all right? Gravity, and what is the acceleration due to gravity on all objects of any mass? It's the same, right? 9.81 meters per second squared. Sorry, 9.80 meters per second squared for you guys. So it doesn't matter the mass because the acceleration due to gravity is the same. So if I pull it out to the same length, each of them accelerates the same way, and so they have the same period. Okay. Now, why does the angle not matter? Well, if we took our pendulum here and stretched it out further, notice that this is an exaggeration, definitely not quite within the 15 meters per second. 15 degrees. Right? In this case, we've still got the force of gravity down and the tension upwards, but what happens to the component of that force there? Well, the component of that force is going to increase with the angle. And so if you have two different amplitudes for your pendulum, if you pull it out this far, it's going to have a very small force to accelerate it back towards equilibrium. If you pull it out this far, instead, it's going to have a much larger force and a much larger acceleration. And what it does, the accelerations will sort of mean that they'll meet up at equilibrium, go back here, and then meet up at equilibrium. And they will always keep on doing this and this. Okay? So, in the end, this is the period of a pendulum. You will see this from your lab if you have not already seen it already, that there is a direct square root proportion from it. And that is the end of class.